Okay, so this time we are going to be just plugging numbers in for x to get out of y. Now this is what's called an exponential function. I know that because the independent variable x is in the exponent, which we haven't really seen before. So it says, go find g of -3. So that would look like this, and that'll be 1 over, 1 over 5 to the third, which is 1 over 125. So that tells us that if we were to graph this function, the point -3, comma 1 125th, that would be on the graph. Okay. And I'll do one more. How about g of -2? So that is going to be 5 to the -2, which is 1 over 5 squared, which is 1/25. So that means that the point -2, comma 1/25 is going to be on the graph. Is there an alternative method, you ask? Of course. So I could go to the calculator, clear this stuff out, and say, all right, well, let's do just do the function 5 to the x power. And we're interested in starting off with x equals -3. So boom, there's everything right there. 0.008, that's 1 over 125. 0.04, that's 1 over 25, and so on. So this is another way to do it. But you need to be able to do it by hand, but also by calculator. Okay, be able to do it both ways. Okay, so for this one, we're gonna graph it by just plotting 5 points. So you can get them off the table on the calculator, or you can just say, well, let's go -2, -1, 0, 1, 2, or something like that. That's just kind of what I usually pick. So, oh, you know what? Let's pick a different color. That's hard to see. So f of -2, looking for the y value, it's going to be -1/2 times 2 to the -2 power, which is going to be 1/8 or 0.125. Okay. Cool. Let's see. Let's do another one. How about f of -1? So -1/2 times 2 to the -1 power. It's going to be -1/4, and that 1/8 was actually negative. Sorry about that. Yeah, it was a -1/8. Okay, then we can go to f of 0. Which is -1/2. We can go to f of 1, which will be -1. And last but not least, f of 2, which will be -2. Okay, cool. Well, the y values are all negative, but they're not, very far away from the x-axis. So let's do something cool here. There's our x-axis. And let's see, let's draw a y-axis. Right, and I'm going to go to, let's make some tick marks. So we got those guys and those guys. Okay, cool. So if we start graphing stuff, yeah, cool. Let's do that. Yeah, that'll work. So the first one says, when x is -2, y is -1/8. So when x is -2, y is going to be about right there. It's only down 1/8. Second one says when x is -1, y is -1/4. So about right there. So left -1, down 1/4. And the third point is 0, -1/2. About right there. The fourth point is 1, -1. And the fifth point is 2, -2. So if I were to graph that, it would look, oh, whoops, forgot I got to turn off the x's. It would look like that. Okay, and that's all you do. And of course, you can always just plug this into your calculator, hit graph, and make sure that what you're drawing on Alex or by hand, matches up with the picture that you expect. Dang, that's definitely one of my better graphs. We should probably just take a moment to savor it and enjoy the moment. Okay, the moment's over. Okay, the dollar value V of t of a certain car model that is t years old is given by the following exponential function. Okay, so before we read the question, or before I read the question, in an exponential function, you always have a number out front, and then you have this number that's raised to the t power, or x, whatever your independent variable is. Now, the number out front, that tells you your starting amount, starting number of rabbits, starting value of the car, whatever. So this car starts out at $24,500. And this number here that's being raised to the t power, the base of the exponent, that one tells you what percent of the current value, which starts out at 24,500, tells you what percent of the current value you retain each year. So you're only going to retain 88% of the value, which means you've lost 12%. Okay, so that's what's going on there. So it says find the initial value of the car. Well, we already know it's 24,500, but initial value means after 0 years, what's the value? Well, anything to the 0 power is just 1, because that's the way it works. And oh, look at that, we get 24,500. Did not see that coming. Okay, so there's the initial value of the car. Then it says, what's the value after 13 years? Okay, so this time, not after 0 years, but after 13 years. Well, it should be lower because it's losing value. It's only retaining 88% of its value each year. Let's see, then we've got 0.8, 13. Okay, pull out my trusty dusty calculator. Oh, I guess I'll just do it over here. 0.88 raised to 13. Okay, and after 13 years, the car still has $4,694.87 of its value. No surprise there. I've been car shopping lately, and yeah, that's how it goes. Okay. Oh, round to the nearest dollar. Okay. Well, then that would be just $46.95. Yeah, because who needs how many cents? Okay. That's how we do it. All righty. So this time we're dealing with radioactive stuff. Okay. Anytime you see radioactive, it's going to be an exponential decay problem. In other words, like the car problem, you're losing stuff, like losing value of the car. But in this case, you're losing, well, it doesn't say what the material is, but you're losing material, the radioactive material. Okay, so you start off with 175 grams, and there's a half-life. They don't tell us what the half-life is, whether it's 10 minutes or 5,000 years. And just to understand half-life, so let's pretend that the white part of this square is how much of the radioactive substance we still have. After one half-life, half of it is gone. And maybe the half-life is 30 years. After another half-life, half of that remaining amount is gone. During the third half-life, the third 30 years, half of that will be gone. So notice, we're not losing the same amount each year, just the same percent, thus suggesting this is an exponential situation. So that's kind of how it goes. So we start off with 175 grams, okay? And they say after 3 half-lives, what's going on? Well, one way to do it would be to say, okay, after 1 half-life, I'm down to 87.5 grams. After another half-life, I'm down to 43 3/4. After a third half-life, I'm down to 21.875 grams. That would be the answer. Now, kind of getting back to what we did in the last topic, another way of exploring this would be to say, all right, so, let's do a y equals ab to the t equation. Okay. Where a is what we start with. Well, we start with 175 grams of this stuff. Okay. And b is what percent we're going to end up with. We're going to end up with half. And so in this case, t stands for the number of half-lives. Not number of years, but just number of half-lives, whatever the half-life is. Again, it might be measured in seconds, years, hours, I don't know. Probably years, but maybe not. Okay. And then that will give you what you want. Because if you want to know y of 3 half-lives, then, one overly laborious way, of writing this out would be to say, oh, I'm multiplying by 1/2 3 times. Okay, it's kind of a silly way of writing it out, but it is accurate. And then that will give you the answer. Now, compare that with what we did on the calculator. Isn't that what we did? We multiplied by 1/2 or divided by 2, did it a second time, did it a third time, just like we were seeing right there. So, same thing. Okay, a study is done on the population of a certain fish species in the lake. Suppose that the population size P of t after t years is given by this function. So this thing is measuring the population in years. Is the population going up or down? Well, the base of the exponent is less than 1, which means it's going down. It means you're ending up with 93% of what you had a year ago. You always end up with 93% of what you had after a year. That's the same thing as losing 7%. Therefore, this would be an example of decay, as in things are going down. Now, if the base of the exponent had been greater than 1, that would mean that, yeah, things are going up and it would have been growth, but, it wasn't. Now, the initial population size, you could plug 0 in for t, say what's going on in year 0, but we already know the number out front that's not being raised to a power, that's always the initial population, or the initial amount. So by what percent does the population size change each year? I don't know. Well, we know that if you end up with 93% of what you had, the amount of change is it's a 7% change, but you're losing 7%. So I'll make the 7 negative. If we were going up 7%, then I wouldn't need the negative sign. Okay. If we were going up 7%, then it would have been 1.07. So 1 plus 0.07 rather than 1 minus 0.07 to get the 0.93. And that's about it for that one, I guess. Okay, now for this one, same topic. This time the initial amount is 1,400. That's the number out front. And this time it is growth because this is bigger than 1. And if it's growth, well, then our percent change is going to be positive. In fact, it's going to be positive 4.9%. Because this guy here is 1 plus 0.049, which means you're keeping your original 100% and adding to that 4.9%. All right, to begin a bacteria study, a petri dish had 3,000 bacteria cells. Oh, cool. Each hour since, the number of cells has increased by 16%. All right, so it's not increasing by the same number of cells, like 16 cells. That would be linear, okay? That would, if it was increasing by, by just 6 cells, then we'd say, oh, this is a linear situation where I'm starting with 3,000, my y-intercept, my starting amount, and things are going up by 16 every hour. So if they just got rid of percent and said cells, that would be the equation. But that wasn't the equation. So we're not going up by the same amount of bacteria, but by the same percent of bacteria. So it's going to be y equals ab to the t. Okay, where a is 3,000, the starting amount, and b is going to be 1 plus 0.16, or just 1.16. Okay, because we're increasing. Now, if we were decreasing, then I would have put a minus sign right there. And that would have been the only difference. Okay, so let t be the number of hours since the start of the study. Let y be the number of bacteria. Write a function. Oh, I already did that. Okay, that would be harder. Or more to do. Cool. Let's try one more of those. Okay, so at the beginning of an environmental study, a forest covered an area of 1,500 square kilometers. Since then, and a kilometer, that's like about 62.5% of a mile, roughly, about 5/8 of a mile. So a little over half a mile. Since then, this area has decreased by 6.75% each year. So it's changing by the same percent, Therefore, exponential. It's not changing by the same number of square kilometers, but by the same percent of what's there currently. Okay. So create a function that represents that. So we need exponential for the reason just stated. And we're starting with 1,500, so that's the A. And B is going to be the original 100%, but we're decreasing, so it's going to be minus, and then 6.75%. And then, of course, you can simplify that to 0.9325, and that'd be just fine. That'd be great. But that's